Hey guys doing? That's good. Here. Let's see. Well, we're going to talk a little bit about schedule changes. Good. You guys kind of jet lagged from the time shift. I like the longer days, the daylight later, but I find the waking up an hour earlier to be harder. All right, we're getting there. Okay. We have some things that are changing in our syllabus, moving some things around. And I went online to our homepage and our syllabus page to make some updates, and our Canvas page tried to make some changes too. So let me actually, I'll write it down, not on here. I'll write it down on a piece of paper so we can have it here that we can see it. All right, so first off, you guys probably got the notice from the provost that they're giving us care days. So we have a couple care days. The first one is March 24th coming up, which is next week. So March 24th, we need to keep in mind. Oh, sorry, that's blurry. I'm trying to get it. Oh, that's even worse. Sometimes my camera doesn't cooperate. Okay, so March 24th. So that's our first care day. So that's Wednesday. So that means no classes. I put this up on our Canvas page too, so you guys can see it. So we had some discussion this weekend or with the other instructors for the calc class about how we're going to accommodate this shift, because there's another care day in April. I think it's is it April 12th? But then we have to go to school. We go to school April 19th, right? Which we used to have this one off, but now we get this one off. So they kind of swapped it. So now, let's see, is that better? I can't tell. Anyway, so now what's going to happen? We have sort of a net gain of a day off. So we needed to change some things around in terms of the topics that we're going to cover. So today, this week, we're going to do 3.1. And then we're going to start, this is today, 3.3, chapter 3.3. And then we're going to finish, this is Monday, sorry, Wednesday this week, we'll do 3.3, and then we'll probably start 3.5, okay? And then Thursday, we'll definitely do 3.5. We may have, we may or may not, you know, get to start 3.5. I'll just put a question mark there. But we'll do the bulk of it on Thursday. I'm kind of allocating Thursday and then next Monday. So this is this week, right? And so then this week we'll have a quiz, and our quiz will be on chapters 3.1 and most likely 3.3 as well. Okay, so you've got homework for this and homework for this. These are all due on Thursday, this Thursday. Okay, this Thursday. Right, and so then next week, right, so next week, basically we're looking at, next week is going to be the 22nd, so 3/22, which is on Monday. So we'll pick up again chapter 3.5, and then we decided that what we were going to do, all the instructors, certainly openly, yeah, I hear you. So what we decided as instructors is that we're going to cancel the section on 3.7, which is mass and density. You know, if we've got time at the end of the semester and we want to go back and do it, I'm totally happy to do it. I took off the lecture examples so we don't get confused, but maybe I can put some stuff at the end. I can put up like the homework questions, the lecture examples for it. You'll notice, I think I'll talk about it in just a minute, but so we have 3.7, and then I had 3.8 up there originally, but there's no 3.8, so I took that off. And then 3.4, I took that off. I had that there originally, but we're not covering those sections this semester. If we have time at the end, which we generally don't, but if we do, I can go back over and do 3.7, 3.4. We can even cover 3.8 if you want. all these things are interesting chapters, but this one we decided to cancel because of time, because of the care days and kind of losing some things we needed to make sure we had them. So just kind of keep it in mind. I've taken these things off of our syllabus so that you don't get confused, and I certainly took them off of the Canvas page too. Anyway, so 3.5 Monday, right? And then we'll do, so Wednesday, which is no classes, no school. And then Thursday, which is 3/25, we're going to do chapter 3.9. So then that week we'll have a quiz on just chapter 3.5 essentially, but so quiz this week will be chapter 3.5 mostly. Okay, so just kind of keep that in mind in terms of, like what's coming down the pipeline to kind of be prepared for. And then we still have our exam is coming up. It looks like our exam, so our midterm, we have midterm number 2. And I know you guys are still waiting for midterm number 1. I am just about done with it. Is chapter 3 about finding area and volume and all? Yes. So chapter 3 is the applications of integration. So we're doing a lot about, it's not just not area so much, that was kind of covered in calculus 1, but we talk a lot about how work, we talk about work and energy, we talk about we used to cover mass, but we're not, mass and moments, and then the big thing is chapter 3 and chapter 3.1, 3.3 are all about distance traveled, position, velocity, things like that. We do that in a straight line, and then we do that in space. So we do parameterized curves, which is chapter 3.3. And then 3.5 is a really big one. That's, we'll do 2 days on that, which is the volumes of revolution, right? So I take an area, between 2 curves, and I rotate it, I revolve it around an axis or a line or whatever. So we're going to learn multiple methods about that. So midterm number 2 is coming up on, I just realized this is the date, it's April 1st. I know that seems horrible to give you an exam on April Fool's Day, but anyway, so this will be mostly chapter 5 and chapter 3. Okay, so kind of keep that in mind. As we get close to it, then I'll put up old exams you guys can study from for that. So midterm 2 is not cumulative, right? It's just basically the stuff that we've covered between the last midterm and when we take this exam for the second one, which is why it's just chapter 5 and chapter 3. But the final exam is for the whole semester, okay? So keep that in mind. Now, I'll write this in a different color. Hopefully this will show up. Something also to take a look at, I have a YouTube page. As you guys know, you guys have been really great about looking at the YouTube page. But on the YouTube page, right, I've got, so I've got the playlist. I've got 2 playlists. Oops, I can spell lists for Calc 2. I've got the Calc 2 lectures, right, which is what I've been posting this semester. And then I've got the Calc 2, it's called example videos. So this is a set of videos that I put up, I can't even believe I'm going to say this, but a year ago when we went on lockdown, I started making videos for like examples. So there's a lot of stuff about chapter 3 in there because we went on lockdown right about now. And so it was basically chapter 3 material that needed to be covered. So there's a lot of example stuff on chapter 3. And then I also started doing a lot of final exam questions. So it was a review for the final exam. So you guys can take a look if you want. It's not required. Like, you don't even have to look at the playlist for the lecture videos, right? Unless you wanted to, because it's the same thing that I'm posting to our Canvas page. But this stuff here is stuff that I posted last year, and it's got some helpful videos on it. Just one note, when a year ago when we first started, I didn't have a whole like big extravagant camera setup like I do now, and so I was trying out different cameras. So sometimes some of the cameras aren't so great. So you may or may not find these videos helpful based on the cameras that are there. So as time goes on these videos, these older ones, the cameras get better and the resolution gets better. Just kind of keep that in mind because I didn't have all the cameras that I do now. Anyway, so it's just something to think about. You can take a look at that if you want to. It might be helpful as an added resource for you. Okay, so midterm in April 1st, and then which is really coming up in like 3 weeks, kind of think about that. And then this week chapter, we're starting 3.1, we'll start 3.3, then 3.3, then 3.5. We're really going to cover 3.5 heavy on Thursday and then Monday. And then we'll do whatever we don't finish on 3.5, we'll do on 3.9. I want to cover some of the homework problems for 3.5 because they're really good questions. Anyway, so just kind of keep that in mind for things that are coming down the pipeline. I think that's about it that I wanted to cover for administrative stuff. You guys good? Okay. So with that said, schedule things. And like I said, I've just updated the syllabus and our homepage, which is also our syllabus too. So you guys can see that. If you forget all the things that I've just said here, it's up there on our in writing. So let's see, let me just make sure that this screen shows everything. And I think that means I can zoom in just a little bit. There. Maybe I went too far. Sorry, it's kind of an art getting the camera just right. Okay. Okay. All right, so let's go ahead and start on chapter 3.1. So when we talk about chapter 3, like I said, this is going to be applied integration is how you want to think about chapter 3. And chapter 3.1, we start off. Chapter 3.1 is called Displacement and Distance Traveled. We're going to cover both these topics here, but chapter 3.1 is moving in a straight line. Okay, so we'll talk about parameterized curves and such when we do the next chapter section 3.3. Okay, so first we're going to draw a picture. So let's talk about our displacement. So what does displacement mean? Displacement, you can think of if you've had physics classes, displacement is our vector, right? So this displacement is a net change in position. So I'll draw it in 2 dimensions here. So I start here, right? And I kind of wander all around, you know, whatever. And I do this in the classroom. I wander around the classroom. And then I end here. Okay. So we do this in different colors here. This path from here to here is my displacement. Right? I start and end. When we think about vectors, right, we go end minus the start. Terminal minus initial is how we calculate our vector. So displacement is just the net. I started here and I wandered all around and I ended there. It's really just this, you know, distance right there. I could start and end in the same spot, right? So I'm just really looking at my start and my end position versus this whole footpath, which is, I don't want red, I want it green, our distance traveled. Right, my total distance traveled as I wandered around. Okay, so this is my footpath, right, and my displacement. So displacement itself, it can be positive, which I'm going to call this negative. Do that, or 0, right? And 0 just means, remember, it's a net change. So if there's a 0 net change, I started and ended at the same spot. Okay, when you think about your displacement. So this is different from what we'll call total distance traveled. And this is, we'll write this out as our footpath. Right, I started at a spot, I kind of wander around. It's that total as I walk all around, you know, how many steps did I take as I walked all around on my footpath. This one, it could be greater than the displacement. And it's positive. It's going to be positive. It's a positive value because it just talks about our total distance traveled, right? Where displacement gives us almost like a direction, like which direction did I go in, right? You think about like your vectors as having a magnitude and a direction. Or displacement could be I moved in the negative direction, or I moved in the positive direction, whereas the total distance traveled is how many feet, how many miles, how many inches did we actually go? Okay, so some notes. If an object changes direction, right? I move on one path, I stop and I come back to where I was and maybe end up in the other spot, or if I go north and then northwest, these two quantities, these two measures will not be equal, right? So they won't, so we'll say our displacement does not equal distance traveled, right? Say I went to the store and I came back home, right? So I drove 3 miles to the store and 3 miles back, right? So my net displacement was 0 because I started at home and then I ended at home, but my total distance traveled was 3 plus 3. Okay, so kind of think about like how our displacement versus our total distance traveled is working. Okay, so for an object moving in a straight line, right, we've got positive and negative directions, right, that we want to think about, and how we denote these things. So let's write our nomenclature. So I'm going to say P of t, right? P of t denotes our position as a function of time. Okay, t usually represents time. Okay, and then we're going to assume that P of t I'm going to assume that P of t is continuous and differentiable, continuously differentiable. Okay, so P of t, position as a function of time. Now, V of t, P for position, B for velocity, denotes the velocity as a function of time. We're going to talk about velocity and speed too. So if you have any questions about that, hold that thought because we're going to get to that. So it talks about velocity as a function of time. And this velocity is the rate of change. Whenever you hear rate of change, you're thinking derivative. It's the rate of change of our position with respect to time. So we're looking at V of t equals dp dt, right? The change in position over time, okay? All right, you guys will have this first page before I turn it. Okay. So how do we get position? We're going to need to integrate our velocity going from time 1 to time 2. Okay. Okay, so depending on how we're integrating our velocity, we're either going to be displacement or distance traveled. But let's talk about displacement first, so I won't confuse you. So we're going to talk about displacement first. So if I go P of t, so P is equal to the integral from t, time, t equals a to t equals b of my velocity with respect to t. And that's PB minus PA, our fundamental theorem of calculus. And I'll put a red box around it because it's important. Okay, and what this tells us here is our displacement from time t equals a to t equals b. right? So as I go between times t equals a, time t equals 0 to time t equals 1 second, what's our displacement, right? For example, okay, we're going to integrate our velocity and we're going to get this without respect to worrying about like signed areas or whatever. We're going to talk about what that means to worry about like if our velocity goes negative, what does that mean in terms of our position? Okay, but let's not get ahead of ourselves. Okay, so integral of velocity gives us our displacement. So this is our displacement right here. Right, I've got my lecture examples for 3.1, right, which I'll post the solutions for those later. So we've got particle moving in a straight line with velocity v of t equals 3t squared minus 12t plus 8 meters per second. What's the displacement? It's important. Make sure you're reading the questions. What's the displacement of the particle between the times t1 and t3 seconds, t2 and t4, and t1 and any arbitrary t? So this one here is going to be an equation. We're going to come up with an equation that basically will tell us, starting at time t to any other time after that, what's our displacement going to be. All right, so before we get started, actually I want to draw a picture. I'm going to do this in green so we can have a nice little contrast. So let's graph our v of t. So this is t. This is v of t. 1, 2, 3, 4, 5, 6, 7, 8. So, right, so 8 is my 4 y-intercept. So I should make this bigger. So I'm going to go 1, 2, 3, 4, so we can see it. Okay, so now what happens, right? I'll do a dot there. We're going to see why I need to come up with like a graph. About here, I think, and then it's going to look like you can plot this out on your calculator too. All right, so so what are we doing? I'm going to go from 1 to 3. So as we go from 1 to 3, so here's 1 to 3. Right, so this is time t equals 1, t equals 3. Okay, that's our first one. Now our next one is 2 to 4. So I'm going to go 2 to 4, right? T equals 2 to t equals 4. So those are the two different things that we're trying to do. And then the third graph is, or the third equation is going to be from 1 to whatever. Okay, we're coming up with an equation for that. Okay, so just kind of keep it in mind. So just looking at the graph, right, we're kind of thinking ahead a little bit, but looking at the graph, right, I've got some areas that are negative, but for displacement, we don't care. We're just going to integrate because displacement can be positive or negative. Okay, all right, so t equals 1 to t equals 3 seconds. Okay, so what do we need to do? I need to integrate. I'm going to go from 1 to 3. I'm going to integrate my velocity. 3t squared minus 12t plus 8 dt. Okay. All right, so let's go ahead and do this. This is just the power rule, right? Pretty straightforward. So this is going to be 3t cubed over 3 minus 12t squared all over 2 plus 8t from 1 to 3. Let's clean this up. So this is going to be t cubed minus 6t squared plus 8t from 1 to 3. Okay, so go ahead and let's evaluate it. So this is going to be 3 cubed minus 6, 3 squared plus 8 times 3 minus 1 cubed minus 6, 1 squared plus 8 times 1. Okay, so when we do this, we're going to get minus 6 meters. Our displacement is negative. Okay, so let's talk about, you know, when you do these, like the homeworks and the quizzes, you just need to give me a number, but I'm going to write down, we're going to put a sentence just talking about it. So minus 6 meters, this is the displacement of the particle between time t equals 1 and t equals 3 seconds. The negative sign means it moved in a net negative direction, right? How we specify our directionality, right? It's kind of arbitrary depending on where we specify our coordinate system, but we have a negative displacement. That means I started and then I ended in a more negative spot than I started in, okay? Between t equals 1 and t equals 3, okay? All right, part A. I'm gonna start scrolling. Part B says, let's do the same thing between t equals 2 and t equals 4 seconds. Because we're just gonna set it up the same way that we did before. Remember our displacement, p of t equals the integral a to b of our velocity. Okay, so I'm gonna go from 2 to 4, 3t squared minus 12t plus 8 dt, which is equal to, I'll skip this intermediate step, t cubed minus 6t squared plus 8t from 2 to 4. Okay, so let's plug it in. 4 cubed minus 6 times 4 squared plus 8 times 4 minus 2 cubed minus 6 times 2 squared plus 8 times 2. Okay, this whole thing is equal to 0 meters. Oops. Okay, 0 meters. All right, let's talk about it. 0 displacement doesn't mean that the particle didn't move, just that it ended up at the same spot it started with. Okay. Give you guys a minute to finish writing that, and then we'll talk about part C, which is time from time t equals 1 to time t equals t, some arbitrary t. Okay. So part C, right, are going to go t equals 1 to time equals t. Okay, which means we're going to get an equation. So how does that look? I'm going to integrate from 1 to t of 3t squared minus 12t plus 8 dt, which is going to equal to t cubed minus 6t squared plus 8t, and I'm going to evaluate it from 1 to t. So this is going to look like t cubed 6t squared plus 8t, right? I plugged in a t everywhere I saw a t, minus 1 cubed minus 6, 1 squared plus 8 times 1. Okay, so really this is affecting a constant term, right? So my final answer, my displacement, is going to look like t cubed minus 6t squared plus 8t minus 3 meters. Right? This here is our displacement as a function of time starting at time t equals 1 seconds until whenever, until t. So we can say, okay, what is the displacement at time t equals 3 between times 1 and 3? I can plug it in and find out my displacement. Okay, so this is displacement. Let you guys finish writing that, and then we'll talk about distance traveled. You guys good? Okay, so displacement, we just integrate the velocity as is, okay? Our distance traveled, remember, we want this to be positive. So when we go to integrate this, we must sum up all the areas under the curve. I guess what we should really say between the curve of v of t and our x-axis, but I'll just say under the curve of v of t. Okay, so which means that I say my distance traveled, I have to watch out for the sign. So my distance traveled is going to look like the integral from time t equals a to time t equals b of the absolute value of my velocity. So it's not enough just to take the absolute value. I have to figure out where things are negative, just the things that are negative, and flip that sign. Okay, that's the algebraic process of taking the absolute value. Okay, the algebraic process is what's negative. It's going to look like this. So for example, I've got the graph like this, the velocity graph that we had before, right? So this area right here was negative, right? This is our velocity on time. So by taking the absolute value, I'm going to go like this. Oop, where it was negative, no, it goes like this. Let me draw that in orange. Like this. And this is our time, and this is the absolute value of velocity. Okay, so whatever was negative is now positive, and then I'm just going to sum up those areas, right? Because I want a positive number for my distance traveled. Okay, so there are steps that I have to follow in order to do this. So let's enumerate what we have to do. So the first thing that we have to do is we must check for intervals of positive and negative in our velocity curve. Okay, we're going to actually talk how we're going to do that, right? So we're going to do an example. We'll go back to our quadratic velocity example. If you have some, with the quadratic, I can find my zero crossings. I can check the sign. If it's negative, I'll just multiply it by -1. If I've got something other than quadratic, right? Well, linear is straightforward, but let's say I've got like a cubic or, you know, exponential or whatever, you can graph this, okay? And then find your zero crossings through your graphing calculator. Just tell me, I use my graphing calculator to tell me what, you know, where the zeros are. Okay, so we have to check for intervals of positive and negative in our velocity curve. So if our velocity is positive, right? So say we're working with this area right here. So if the velocity is positive, then we're going to integrate normally. Right? It's going to look like I'm just going to go from A to B, sorry, B of t dt. No big deal, right? So let's say, for example, this is positive. This is positive right here. Okay, so this is this region, right? So we're talking about if it's positive, okay, then just integrate normally. We're trying to get the area between our function and the x-axis. Okay. If our velocity is negative, like we showed in orange here, so if the velocity is negative, right, then what do we need to do? Then we have to integrate -1 times the integral of our velocity. This is how we are making it positive. All these numbers are negative. If I multiply them by a negative number, I make them positive. Okay, doesn't change the values, it just changes the sign. Okay, multiply by a negative number. Okay, and we're going to talk about how we do all this stuff. If v of t is mixed intervals of positive and negative, then we have to break it up into multiple integrals, right? I'm going to combine these, so I'm going to add them together, right? Then we're going to break up integral into segments, right? So I'm going to add the positives and the negatives together. So I'm going to go from A to C, my velocity, where it's just positive, plus a -1 times C to D of my velocity. And this is from A, I should make C to B. Let's call it B because we're going from A to B originally. Sorry, let me make that clear. A to B. And this is how we're taking the absolute value, and this gives us the distance traveled. Total distance traveled. So I'll put a red box around that. So this is positive, this is negative. Okay, so we have to check for areas of positive and negative. You can graph it on your graphing calculator, take a look. Whoops, sorry, my camera's. You can graph it on your graphing calculator, take a look and see, do you have things? Because if like our parabola is floating above the x-axis, it's all positive, then I'm good to go. I don't have any zero crossings, it's all positive. If it's all negative, then I just multiply everything by a negative number, right? And then work it from there. It's when velocity goes from positive to negative, right, that I need to do this part right here. Then I need to break up my integral. Okay, let you guys finish writing that. And then I'll go back to the lecture examples where we look at the same velocity equation, but now we're going to talk about distance traveled. Okay, you guys good? Okay, so here I am on example 2. So particles moving in a straight line, we have the same velocity that we did before, right? Same equation. What's the distance traveled between t equals 2 and t equals 4? So I'm going to go back to look here. So remember our graph, right? So we're looking here from 2 to 4. So I've got some areas of negative, some areas of positive I need to take into account, right? So we already knew kind of from looking at the graph that we're going to have positive and negative stuff that we had to worry about. So now I have to figure that out, right? So I'm going to go from 2 to 4, absolute value of my velocity, whoops, dt. Okay, so I have to split up integral into positive and negative segments. My handwriting is really bad, sorry. Okay, so let's do it in steps. Step 1, we're going to factor d of t equals 3t squared minus 12t plus 8, right? Because what we want to do is we want to be able to figure out where are the intervals of zero crossings, right? So if I get an imaginary response out of this, then I know it's not passing through the axis, and I just have to figure out the sign, positive or negative. So this is the algebra part, right? I mean, if I had just graphed it on my graphing calculator, I can see, I can probably get my zero crossings, my zeros out of my graphing calculator, but let's go through the math, how we're going to do it. So we're going to factor this, right? And I'm going to use the quadratic formula. It's just going to take me right to what my x values are that give me when x equals this, y equals 0. So my quadratic formula, minus b, minus 12. So minus and minus, so that's positive. Plus or minus b squared minus 4ac, all inside of a square root, all divided by 2 times a. So this is going to give us, this is a function of t. So this is going to give us, I won't write all the steps of how this all works out, but this will be 2 plus or minus 2 radical 3 over 3. Now, for accuracy's sake, when I go to integrate, I'm going to leave it here in simple radical form because I want my integral to be specific. But this is roughly 0.8 and 3.2, right? Which we can see on our graph. I do the dot just a little before 1 and just a little bit after the 3. Okay, so but I'm going to use this here, this number here in my integral. Okay, so that's step 1. Step 2, so it passes through the x-axis, but I have to know, is it positive or negative? So step 2, I have to find areas of positive and negative, right? Which means I'm going to check my endpoints. Check endpoints of interval 2 to 4, right? So I'm going to plug 2 into velocity, right? So velocity at 2. So I've got 3 times 2 squared minus 12 times 2 plus 8. I calculated all to get minus 4, which is negative. Okay. At 4, I'm going to go 3 times 4 squared minus 12 times 4 plus 8. I got a positive 8, which is positive. Okay, so I'm changing sign, which, you know, we figured it was going to happen. So I'm changing sign within my interval, right? So just as an FYI, 0.8 is a place where we're changing sign, but it's outside of our interval, so I'm not going to worry about it. But I'm changing sign at 3.2, and it looks like I'm going negative to positive, right? Because I knew I was going to have a zero crossing, but I'm going negative to positive. Now, if I had, like if this was, you know, cubic or quartic or whatever, and I had multiple, within my interval, I had multiple values, I'd have to check on either side, right? It just so happens that 2 and 4 sandwich 3.2, right? So I only have to do one check at 2 to 4. But if I had many of these, you know, roots, or it's going to pass through the x-axis within my interval, I need to check all of them, their signs, to see which direction they're changing sign. Okay, because it's the negative ones that I need to change to make them positive. Okay, so our velocity switches sign at t equals 2 plus 2 radical 3 over 3. This is our approximately 3.2. Okay, which means, oh, and that's right, clarify, in this interval. Okay, so in this interval, we've got one value of t where it's changing sign. Okay, so step 3. Right, what do we need to do? We need to break the integral into 2 parts, the positive and the negative part, right? So my negative part is at the beginning. So I'm going to go minus 1 times, I'm going to go from 2 to 2 plus 2 radical 3 over 3. And this is going to be 3t squared minus 12t plus 8 dt. I've got a negative 1. I choose to distribute my negative 1 into all these terms and then integrate so I don't forget. And then I have plus, right? The other part from here to 4 is positive. 2 plus 2 radical 3 all over 3 to 4, 3t squared minus 12t plus 8 dt. Okay, so I've got my integral. I've broken it up into 2 parts. Then we just get to integrate it and evaluate it. Okay, you guys have that? I'm going to turn the page. All right, so step 4. Integrate and evaluate. Okay, to get the total distance traveled now we're talking about. All right, so let me rewrite this. So I'm going to go from 2 to 2 plus 2 radical 3 all over 3. I'm going to distribute my negative minus 3t squared plus 12t minus 8 dt. So I distributed that negative 1 plus 2 plus 2 radical 3 all over 3 to 4. 3t squared minus 12t plus 8 dt. Okay, so this is what I just wrote on the previous page. Okay, now I'm going to integrate. Okay, so this one becomes minus t cubed plus 6t squared minus 8t, going from 2 to 2 plus 2 radical 3 all over 3. Plus my other one, t cubed minus 6t squared plus 8t, going from 2 plus 2 radical 3 over 3 to 4. So now I have two different pieces I need to evaluate. So let's do them in parts, not integration by parts, but evaluation in parts, so you can keep straight. Okay, so this part we'll do first. Minus 2 plus 2 radical 3 over 3 cubed plus 6, 2 plus 2 radical 3 over 3 squared minus 8. Try not to round ahead of time because you're going to start accumulating rounding errors. That's why I kept it as the simple radical form. You can just plug it in your calculator as radical, right? At the very end, we'll round our answer. Okay, so this one there, minus 2 cubed plus 6, 2 squared minus 8 times 2. Okay. I'm going to skip all of the nitty-gritty algebra details of combining all these things here. Okay, and what I get is 16 radical 3 all over 9 for this bit. This portion here, oh, I'm going to lose my spot. Sorry, I'm going to cut right down through here. I hate doing that, but I'm cutting right down through here. This bit here, we're going to go 4 cubed minus 6, 4 squared plus 8 times 4. This is plus. Minus 2 plus 2 radical 3 all over 3 cubed minus 6, 2 plus 2 radical 3 all over 3 squared plus 8, 2 plus 2 radical 3 all over 3. So this is going to be, in the end, plus, oops, this is going to be equal to 16 radical 3 all over 9. So let's summarize both pieces. Okay, so in color, that's this one. And in color, that's this bit. So this is going from 2 to 3.2, and this is 3.2 to 4. Okay. Here, and I'm going to get 32 radical 3 all over 9, which is approximately 6.1584 meters. This here is our total distance traveled, our footpath. Between t equals 2 and t equals 4 seconds. Okay. So far, so good. All right, we're using our ideas of integration, right? Our methods of integration to help us. But what you need to remember is our total distance traveled, I have to take the absolute value of it. But it's not just as simple as taking the absolute value, like my answer. I have to do this ahead of time. I have to identify areas of my curve that are negative and multiply them by -1 and integrate that. You have to identify areas that are positive and integrate them normally. Okay, so be very careful. You can't just like integrate it between 2 and 4 and take the absolute value. You want to be doing the absolute value ahead of time. You want to be taking a look very specifically about the intervals that are going to be negative and positive. Okay. So last ideas, these are a little bit lecture notey, but I'm going to put them into our lecture examples so that we all have them in one spot. So kind of a summary here. Let's think about our average speed, right, which is going to be, let's say, from t equals 2 to t equals 4. So our average speed is our distance traveled divided by our change in time. Okay, which means the distance traveled between 2 and 4 seconds is 6.1584 meters. We just calculated that. And we're going from time 2 to 4. So I'm going to do B minus A. This is seconds. So then what we get is 3.0792 meters per second as an average speed. Okay, so speed is related to distance traveled. Speed is like a scalar, right? So this is going to be positive. What's our average speed? Let's see, this is our displacement. Remember, this is just remembering from example 1. T equals 2 to t equals 4 was equal to 0. This is example 1, that we did that before, right? So we want to do average velocity. Okay, I'm going to say that's my displacement. Velocity is a vector. So I'm going to do displacement all over delta t. This is my average velocity. So I'm going to go 0 meters all over 4 minus 2 seconds. So what do I get? I have a 0 meters per second average velocity. Okay. Anytime we're taking an average, we're doing this. From A to B, dt, right? So this is going to be our, this is for displacement. And then, or I'm taking the absolute value. And this is for our distance traveled. Right, so this is our average velocity, average speed, okay. Let's do a quick summary. So we have it in one spot. Okay, my displacement. I know we kind of wrote it here, but let's write it out again. Our displacement is going to look like, I'm going to integrate our velocity as is, P of B minus P of A. Okay, our total distance traveled. Right, we're going to go from A to B, absolute value. And remember the process of taking the absolute value. It was step number 1, step number 2, step number 3, and 4. We have to figure out where, if anything, we have zero crossings. We have to find areas of positive and negative. We have to multiply the negative areas by -1 to make them positive, and then we get to integrate and sum everything up. Okay, so that's 3.1. Right. So what I'd like to do is, we're just going to start. We'll spend the next 5-10 minutes talking about 3.3. We probably won't even get to our lecture examples for 3.3, but I want to just start the ideas. Okay, so I'll post these later so you guys can have them. All right, so 3.3 is similar to chapter 3.1. So this one is distance traveled in space. And it's like displacement in space too. And arc length. Okay, so, well, like, weren't we traveling in space before? Well, no, this one is going to be, we're talking about parameterized curves. Okay, so, right, where I've got our function, our x position, our y position, and possibly our z positions are all functions of time, right? So our x, y, and z are all functions of time. We're going to write this again down again, so don't worry about it. So we got parameterized curves, but let's just draw a picture because I like these pictures. So let's say I start here. So this is my position at time t equals 0, time t 0. And then I kind of meander around and then I end here. So this is my position at time t1, right? So this right here is our displacement. And this is our distance traveled. This is like what we just did just now in chapter 3.1. Okay, but now when we talk about parameterized curves, right? Let's do this. So I've got C at 0. And then I have my displacement, C at time t equals 4. And then I've got my path traveled. Here, our curve, okay? And our function C of t has an x function and a y function. So this is our x position as a function of time, and this is our y position as a function of time, okay? So what this does is it kind of takes x and y, you know, and it says, well, we can then just separate out. We can talk about our horizontal and our vertical, say for example, or our x, y, and z positions, you know, as functions of time. It allows us to break things apart. So now C is actually a multi-component function, right? I'll talk about what that means in a minute, but we've got an x and a y component that I need to be thinking about. Okay, so let me start writing some words. So our object is moving, but not in a straight line, like we did in chapter 3.1. So we must parameterize the curve. Okay, we're actually going to give you the parameterized curve, okay, and then you're going to be working with the parameterized version. I think some of your homework problems are going to ask you for stuff, you know, in relation to others, but basically you're dealing with parameterized curves at this point. Okay, so our position function is now a vector, okay, in which the x, y, and maybe z, right, depending if we're in 2 dimensions or 3, okay, in which the x, y, maybe z components are functions of a parameter. This usually is represents time. Okay, may represent time. So what does that look like? So in 3 dimensions, which we write fancy R with a 3, okay, this means all real numbers in 3 dimensions. Right, so I've got x, y, and z axes, okay? Negative z, negative x, negative y, okay? So my 3 dimensions, I'm gonna write it like this. Okay, this thing here, this little arrow over the top, means it's a vector, which means it has direction and magnitude. These are like vocabulary ideas that we're going to talk about on Wednesday. So P of t, I have x of t, y of t, and z of t. Okay, so x of t is the x position as a function of time. Y of t is the y position as a function of time. And then z of t is the z position as a function of time. These are all functions. Okay, so I can do function stuff on them. I can integrate, I can derive, take the derivative, all sorts of stuff, but I'm going to do it in place. Do stuff, and I'm going to keep it in its x spot. I'm going to do stuff here. I'm going to like take the derivative or the integral, and I'm going to keep it in that spot. Okay, so we think of P of t is defined, continuous, and differentiable. We're going to make this assumption, differentiable on the interval a to b. Okay, which means that my derivative, right, is also continuous. Okay, on A to B, and differentiable on A to B. Okay, and then we're going to go into details about what this means tomorrow. We're going to talk about this tomorrow, Wednesday. Okay, so we're going to go into details about how I can take this derivative when I've got this function and this function and this function, right? And it's really straightforward. I'm just taking the derivative here and I leave it in its x spot. I take the derivative of this function and I leave it in its y spot. I take this derivative of my z function and I leave it in its z spot. Okay, so it's just straightforward. We're just going to deal with them in place. Okay, but these are vector functions, right? They have magnitude and direction. We're going to talk about how we calculate those things. Okay, and they are multi-component functions, but they're all a function of time. Okay, the same t parameter operates on x, y, and z. Okay, guys. Okay, so Wednesday, right, we'll pick up on 3.3 and then take a look at the homework for 3.1. At the end of class on Wednesday, maybe we'll have a few minutes to answer some questions on 3.1 homework. Okay. Have a great day, guys. I'll talk to you later.
Thank you.
Bye, guys.
Thank you.
Thank you.
Bye. Take care.
Thank you.
Take care.